especially in the X-ray, but all bands too. And he had been in Penn State for 25 years after graduating from the University of Cambridge and a postdoc at CFA Harvard. So his specialty is active galaxies, and again, all bands, but mainly on the X-ray. So he's going to talk to us today about the growth of supermassive black hole. Neil, the floor is yours. Thank you.
Great. Thank you. Thank you for having me. I'm glad the technology is working well this week. That's great. So today, I would like to tell you about the results from cosmic X-ray surveys of the distant universe. We have been blessed over the past couple decades to have several superb observatories for such distant universe surveys, including the Chandra X-ray Observatory, XMM-Newton, NuSTAR, shown here, as well as other facilities like SWIFT, and for a brief time we had, of course, eROSITA. Today I am going to focus on the results from these three missions here. They all work together effectively, complementing each other. Each one has its own individual strengths. For most of the talk, I will likely focus on results from the Chandra X-ray Observatory and XMM-Newton, but I will also bring in connections with multi-wavelength observations, with future facilities like the Rubin Observatory and LSST, and so on. During this talk, I'm going to talk about surveys like the following. I will talk about the results from the Chandra Deep Fields, which are the very deepest X-ray observations we've ever made with the Chandra X-ray Observatory. And then I will also talk about a much wider field survey, this one here, the XMM-SERVS survey, which we have recently completed, which has covered much of the Rubin LSST Deep-Drilling Fields with sensitive X-ray coverage. And this is a much wider field survey than this one. In fact, this white circle here is large enough to cover the entire Chandra Deep Field-South, which is embedded inside this wider field region here. And so these images here are certainly not to scale. And, you know, as per the title of my talk, I am going to speak about the supermassive black holes we detected in these surveys as revealed by the study of active galactic nuclei, or AGNs. That will be the overall focus. So I have many people to thank. Over the past 25 years, I've worked with a number of excellent Penn State graduate students, most of whom are still in the field around the world. I've also worked with many great postdoctoral researchers. It's been a great pleasure to work with all of these people. They deserve a lot of the credit for the things I'll be discussing today. And then, of course, I also want to thank many great collaborators worldwide. These are two papers presenting the source catalogs for these surveys. So they almost all the people who were involved are co-authors of these papers. And we have collaborators from around the world representing these countries listed here at the bottom. And so today, for the talk, I would like to start off by briefly covering the general utility of X-ray surveys of active galaxies. Why is this a valuable thing to be doing? I'll then tell you about the Chandra Deep Fields. Again, the very deepest X-ray observations we've ever made. I'll talk about some selected science results from the Chandra Deep Fields, just a couple of examples. And then I will talk about the XMM-SERVS survey, its relation to the Rubin Observatory and the LSST Deep-Drilling Fields, and I will talk about future prospects. So that's the overall plan. So let's start with the utility of X-ray surveys of AGNs. So we know that the X-ray emission from active galactic nuclei is nearly universal. We've studied large numbers of active galaxies selected in a variety of different ways, and they almost always show strong X-ray emission. This X-ray emission, we believe, originates from the immediate vicinity of the black hole, as shown in this artist's impression here. We believe there is a coronal structure, perhaps similar to the sun's corona, shown down here in the lower left. And the X-rays are made when ultraviolet and optical photons from the accretion disk are Compton upscattered by a hot billion Kelvin coronal structure. And that Compton upscattering boosts the optical and ultraviolet photons to become X-ray photons, and that's what's producing the X-ray emission that we observe. The overall spectrum that is produced generally for an active galaxy in the absence of any obscuration looks like the following. You have a broadband continuum spectrum. You sometimes have specific line features. Here is the iron K line in the X-ray band. This is made when X-rays shine down upon the accretion disk and interact with the accretion disk. And and so on. And the technical details of all the various technical aspects of the broadband spectrum aren't what's critical here. It's just to get a sense that this is a broadband continuum. Note that this X-ray continuum is spanning 3 orders of magnitude here just in the X-ray band. So this is much, much broader than the optical spectrum. We have a very broad grasp upon the AGNs SED, or spectral energy distribution, in the X-ray band. And for reference, Chandra and XMM-Newton deep surveys typically detect sources between about 0.3 and 8 keV. So we're kind of working in this band here. And then NuSTAR, its main thing is it extends sensitive X-ray imaging up to somewhat higher energies. It extends it up to about 16 keV or so effectively for these deep surveys. And so that's the kind of band that we're observing in. This is somewhat lower energy than the medical X-rays that are used in your doctor's office or your dentist's office. Okay. So that's one point. The universality of X-ray emission from active galaxies is very important. Secondly, as we all know from the doctor's office and the dentist's office, X-rays are a highly penetrating form of radiation with reduced absorption bias. That's extremely important because we know that the light from an active nucleus down in the center of a galaxy is usually substantially obscured, both by material in the immediate vicinity of the black hole as well as by galaxy scale material. And the point is that X-ray emission can penetrate through and also allow measurements of large amounts of obscuring material that are present in these systems. And that's what's being shown here, where essentially I've taken the exact same plot I just showed you back here and I've turned it into a little movie. And what I'm doing now is I'm adding obscuration to the spectrum. This is the column density of hydrogen that's being added. And you can see that as you add absorbing material, you get a systematic absorbing away of the low energy X-rays. And that systematically marches up in energy as you raise the column density. And for point of reference, the column density through your hand is about 10 to the 23. The column density through your chest is about 10 to the 24. Okay, and so that's kind of lets you relate what the phenomena you're seeing here to to active galaxies. Okay, another great point about X-ray observations is that the absorption bias drops as one goes to higher redshift. As one observes higher and higher redshift AGNs, this whole spectrum is cosmologically redshifted downward in energy. And so in a fixed observed frame, you gain access to increasingly penetrating rest frame X-rays. And so for the surveys that I'm doing, where I'm typically studying sources at a redshift of 1 or redshift of 2 or 3 or even beyond, I'm accessing very penetrating X-rays. There you actually are reaching up in the rest frame to medical X-ray energies, highly penetrating X-rays. And not only can you punch through the obscuring material, but you can measure how much of it is there by measuring exactly where this cutoff is. So we can measure absorbing material as well. Okay, and then finally, the third reason why X-rays are a very powerful way of doing surveys for active galaxies is they have low dilution by host galaxy starlight. And that is shown here. This is a local active galaxy. Here I show the optical image of that galaxy. Here I show the X-ray image. I haven't done any tricks with the scaling or anything. And the point is that all the starlight drops away in the X-ray band, and you just see the black hole related light from the nucleus. And that's extremely important for the high redshift studies that I'm doing, where galaxies are very small on the sky, because you can't spatially resolve away the AGN light from the host starlight at high redshifts. You need a form of radiation that maximizes contrast between black hole related light and starlight, and X-rays gives you that very high contrast. Now, of course, X-rays by themselves aren't perfect. Best of all is to combine the X-ray methods with multi-wavelength methods, and that is in fact exactly what we do. So those are the three reasons why surveys are really great. X-ray emission appears to be nearly universal from active galaxies. It's highly penetrating and it has low dilution. And those three basic facts have led to a whole industry of X-ray surveys being done. This plot here from a recent review article that's just been published properly just a couple of weeks ago, in fact, shows the flux limit versus the solid angle for a selection of X-ray surveys that have been done by Chandra, colored blue, XMM-Newton, Rosat and Einstein, that's earlier X-ray missions, as well as recently eROSITA. And you can see that Chandra is superb at covering the very highest sensitivities, very lowest fluxes. XMM-Newton is superb at kind of moderate depth, moderate area surveys. eROSITA is now the best at very wide field surveys. And so all of these missions together, all of these surveys are used together to place constraints upon black hole growth in the universe. And that's exactly what we're doing. Okay, so that's the motivation for why X-ray surveys are a worthwhile endeavor. Now I'd like to tell you about my probably still personal favorite examples of X-ray surveys, and that is the Chandra Deep Fields. So the Chandra Deep Fields, going back to this plot, are the extreme in small solid angles, so kind of pencil beam, ultra deep surveys. We've conducted two of them. I'll show them to you now. We've conducted one in the northern hemisphere. It's kind of near the Big Dipper up on the sky. And then we have one in the southern constellation of Fornax. And this one's the Chandra Deep Field North. This one's the Chandra Deep Field South. For this one, we have about a 2 million second observation with Chandra in total, gathered over about 2.5 years. This one, we now have 7 million seconds gathered over about 16 years. These cover about 60% the size of the full moon on the sky. These are the numbers for the solid angle coverage. And we detect, well, 755 point light sources here, 1,055 point light sources here, the majority of which are active galactic nuclei. These are the percentages here. And another thing I want to highlight is that the X-ray detectors, the CCD-based X-ray detectors that we use on these missions are not only making images. We don't only have images of the sky for these regions. We actually, for every single photon, measure its energy and its time of arrival. So we also have spectroscopic information and variability information. So this is true imaging plus spectroscopy plus variability all in one shot. So we can pick any one of these sources, we can cut it out, measure its X-ray spectrum, measure how it's varied over a long period of time, and we use all of that, in fact, to understand these sources. And another point which I always find remarkable is that the faintest sources down here in the central part of the Chandra Deep Field-South, and now I'm going to zoom in on this little box here, that the faintest sources we detect down here, right in the very center of the Chandra Deep Field-South, this is where we have the very most sensitive X-ray coverage, are such that we get on average about 1 photon coming in every 10 days. And so that shows how amazingly well Chandra has been built, that you can detect sources where you get 1 photon every 10 days, and those sources are still easily detectable above background. And so Chandra has been built remarkably well. This plot here is of course color-coded according to the X-ray energies using the spectral information that we have. This is the color coding. And this work, this cataloging work for the Chandra Deep Field-South was led by my very successful graduate student, Bin Luo, who is now a professor in Nanjing. Okay, so in addition to the X-ray coverage, we of course also have superb multi-wavelength coverage of these same sky areas. We deliberately chose to do the Chandra Deep Field-South, for example, in the region where there is extraordinarily sensitive, for example, Hubble Space Telescope data. This is the ultra deep Hubble data in the Hubble Ultra Deep Field down in here. And this is the gray here shows our X-ray image. Here's the Hubble Ultra Deep Field. There is also extraordinary Hubble imaging with the GOOD survey, with the CANDLE survey, with the 3D HST survey over a much wider part of our field. And notably, in fact, if you add it up, in fact, about 70% of an entire Hubble cycle, corresponding to about 6 megaseconds of Hubble time, has now been spent just in this sky area. And if you price that out over Hubble's lifetime, that's about a $250 million investment of Hubble time that's been sunk into this field. So there are extraordinary high quality multi-wavelength observations, and I'll show you how we use those in just a minute. And of course, extensive coverage from the James Webb Space Telescope is, well, currently being gathered, and so that will soon be available to use to understand the X-ray sources as well. Now, in addition to the Hubble coverage, we also have a lot of other critical multi-wavelength observations. The largest ground-based telescopes have conducted extensive spectroscopic campaigns on these fields. There's very sensitive, for example, ground-based near-infrared imaging. Spitzer and Herschel have covered the near-infrared and the far-infrared to very high sensitivity. There is superb sub-millimeter observations over the field. There is also superb radio observations, and all of this multi-wavelength data is critically important for source identification, just figuring out what the X-ray sources are, what they match to, classifying them, understanding their nature, measuring their host galaxy properties, and so on. And because the X-ray data have gotten better over the years, and because the multi-wavelength data continue to get better over the years, that's what's kept this whole thing exciting, for a couple of decades now. To show you how we're doing with counterparts and redshift, right now for the Chandra Deep Field-South, for example, where we've put in the most effort recently, we now have 98.4% of the X-ray sources where we can find counterparts to them. Okay, so we have a very high completeness on counterparts. And remarkably now, 97.8% of the X-ray sources have redshifts. Okay, so we have very good redshift completeness. There's been so much spectroscopic time sunk into this field by, for example, the VLT and also CAC, that we actually have the majority, about 65%, being spectroscopic redshifts. And then about 33% are photometric redshifts, but these are extraordinarily high quality photometric redshifts derived from like 30 to 40 bands of coverage. This is our typical photometric redshift uncertainty and our outlier fraction, which is very good. So we have a good, complete set of counterparts and redshifts for all the X-ray sources, so we can use that to trace black hole growth over the history of the universe. This is our redshift distribution for the AGNs that I'm focused on in red. Here is our distribution. You can see we span about redshifts of about a half up to redshifts of about 4 with pretty good source statistics. So we're spanning a good wide range of cosmic time. And this here shows the redshifts in narrower bins. And you can see we actually are tracing cosmic structures via these redshift spikes that we get in the X-ray sources. Okay, so now I want to show you some of the X-ray sources. What are they like? What are the sources that make the cosmic X-ray background? Well, these are the sources that do it. This is a plot that shows, in each case, each one of these panels shows the Hubble image of the counterpart of one of our X-ray sources. These are 12 arcsecond by 12 arcsecond images made from a combination of B, Z, and infrared coverage. And the circles show the 68% confidence error circles of the X-ray sources. And because Chandra has excellent imaging and gives very high quality source measurements, you can see we can identify counterparts quite reliably. And we have active galaxies ranging from very faint sources like this one. This one's at a spectroscopic redshift of about 3.7, up to much brighter local objects at a redshift of 0.23 in this case. And we have large numbers of panels like this that let us characterize the sources statistically. And that's what we do to set valuable statistical constraints about where black hole growth occurs in the universe. We use characterizations of large numbers of sources like this. To show you some more, here's another panel. Okay, here's another panel. Here's another panel. And in total, I have like 20 panels like this, showing all the X-ray sources, with their detailed, morphological and spectroscopic characterizations. Okay, so now what I want to do is talk to you about some selected science results coming from the Chandra Deep Fields. This, of course, cannot be comprehensive. I'm just presenting a couple of highlights from recent work. And there's much more that I cannot present today, but which you can look at if you're interested. First, I would like to say a little bit about recent efforts we have made to constrain what matters for long-term cosmic supermassive black hole growth. There are many possible things that could affect how a galaxy grows its black hole. It may be that massive galaxies with large stellar masses, tend to grow their black holes better. We, in fact, have good evidence that's the case. It could be that star formation rate links to black hole growth. It could be that galaxy structure, whether a galaxy is highly compactified in its center or not, links to black hole growth. Or it could be that a galaxy's environment links to black hole growth. And so two students that I've recently had who are both excellent, Guang Yang and Qingling Ni, have written PhD theses on addressing this broad topic. There's about 5 or 6 papers, which I can't all cover in full detail today, but I'll just go show you a couple of highlights. Now, one thing that we have had to do when addressing this question of what matters for long-term cosmic black hole growth and how it connects to these quantities is you have to think very carefully about what the X-ray data actually mean. So often when I look at this image of the central part of the Chandra Deep Field-South, I ask the question, well, what would this image look like if we did the experiment, not now, but if we did it, say, in 1 million years or 10 million years or 100 billion years? Would it be the same exact pattern of spots, X-ray emitting spots up on the sky? Or rather, should this properly be interpreted instead as a statistical sampling of the types of galaxies that tend to grow their black holes? And there's much evidence, given from what we know about X-ray variability of active galaxies, that this is the right perspective, that you can't interpret the exact pattern of spots as being fundamental, but rather you should think of this as a statistical measure of what types of galaxies like to grow their black holes. So what we then do to address this question in red here is we take galaxies with a specific range, say, of stellar mass, or a specific range of star formation rate, or structure, or environment, and we average galaxies, say, of a given range of stellar mass, to be specific. We average the observed X-ray emission, tracing the black hole growth across a set of galaxies that has a certain range of stellar mass, and that kind of time averages out the effects from the variability. In other words, we consider the black hole growth to be ergodic, so that we can replace a time average with a sample average, and that's what we're doing here, okay? Now, the second point I want to make is that we have good indications that morphology or galaxy structure is going to matter a lot for black hole growth. And that's, in fact, what I'm going to talk about today. And we have evidence from that from relations like this, where we observe that the mass of black holes in the local universe strongly correlate with, for example, the luminosity of the bulge and the velocity dispersion of the bulge. But when you look at other measurements of galaxies, like the galaxy's total stellar mass, shown here, or the galaxy's disk luminosity, the correlations are much, much worse. So you get clear linkages between black holes and bulges. You do not see linkages between galaxies in general, or if you do, there's a lot more scatter. There's a broad correlation there, but there's a lot of scatter, or between galaxy masses and disk masses, black hole masses and disk masses. So you have to be a little careful here considering morphological effects. And so that's where we rely upon the Hubble data. And what we're essentially trying to do is to measure the time derivative of this diagram, because we'd like to see this diagram being built up in the distant universe. So the time derivative of a black hole's mass is the black hole's accretion rate. The time derivative of a galaxy's bulge luminosity or bulge mass is the star formation rate of the bulge. And so that's what, in fact, what we try to do. We try to measure black hole growth from the X-rays. We try to measure bulge growth from the star formation rate, and this is how we've been doing it. So what we've had to do so far is we separate our samples of galaxies into bulge-dominated galaxies, and these top 2 panels framed in red show the bulge-dominated sample. This has been selected from 10,302 galaxies taken across 5 Candles fields, including the Chandra Deep Fields. And we utilize machine learning morphological measurements made out of the H-band. So you're measuring rest frame optical light made by Huertas Company et al. And again, we separate galaxies into bulge-dominated systems, these 2 red frame panels, and then non-bulge-dominated systems like these 2 bottom panels framed in blue. The key idea here is to remove non-bulge components because they don't seem to correlate with black hole growth. So we're trying to home in on galaxies that are bulge dominated to try to limit effects from non-bulge components in these galaxies. Or in other words, so that, for example, the bulge star formation rate is very nearly the total star formation rate of the galaxy, because that's the thing that we can measure using, for example, the infrared coverage and the ultraviolet coverage. So then, when we do our best to measure the bulge star formation rate and the black hole growth via the methods I've just described, this is what we find. We find that the black hole accretion rate does correlate with the star formation rate of the bulge-dominated sample. The correlation is quite clear and strong, and we find it at redshifts of 0.5 to 1.5, and at redshifts of 1.5 to 3 and 1.5 to 3. So we see that, oh yes, you can actually see the lockstep growth of black holes and bulges in the bulge-dominated systems. For comparison, if you look at the non-bulge-dominated systems, the correlation is much less clear. And we attribute that to the fact that there are lots of non-bulge components present in these galaxies, and they don't link to the black hole growth. There is some correlation there, as there should be, because these galaxies do have bulges in them, but they have other components as well. And so that messes up the strength and the clarity of the correlation that we observe here. Now, not only can we deduce that there's a correlation there, we can measure the correlation quantitatively. And this is basically the relation that we find. We find that the black hole accretion rate is equal to the log star formation rate with an offset in the log of minus 2.48. That corresponds to a black hole accretion rate to star formation rate ratio for bulge-dominated galaxies of about 1 part to 302. Which is similar to the ratio of black hole masses and bulge masses in the local universe. It's not exactly the same, but it's within a factor of couple. It's similar to that. So we take then these measurements to be evidence for genuine co-evolution over cosmic time of black holes and bulges, because we observe directly the apparent lockstep growth via these correlations. Other people have proposed that there may be just a merger averaging effect that leads to this correlation, and our measurements do not support that. We actually see evidence for direct lockstep growth of black holes and bulges. And we are presently working to constrain this topic further. There are questions as to whether this result leads to the actual production of this relation, or whether it just maintains this relation over cosmic time. And we are working to constrain that right now via ALMA measurements, and we hope to use James Webb Space Telescope measurements in the near future to extend this work. You can see some of our work from a recent paper published by Yang et al. In 2022. So that's one result that we got, which we think is pretty interesting. We also, continuing on this theme of connections to morphology, we've also have looked at other possible morphological connections. For example, Qingling Ni has led some important work investigating the connection between black hole growth and the compactness of a galaxy. And we find that black hole accretion rate shows clear connections to galaxy compactness, at least among star-forming galaxies as well. Compactness essentially is a measure of the mass to size ratio of a galaxy. Galaxies that are like this are not very compact, and as you move this way, galaxies are becoming progressively more compact. Okay? There are a variety of measures people use for galaxy compactness. This is the one that we actually find correlates the best with black hole growth. It's essentially a measure of the stellar mass in the inner kiloparsec of a galaxy. Okay? And we find that at least for gas-rich star-forming galaxies, this sigma-1 quantity may also serve as a tracer of central gas density on a kiloparsec scale in a galaxy, which would lead to the feeding of a black hole. And so we've measured compactness in the rest-frame optical using Hubble Space Telescope data from Cosmos and CANDLES. And when we look at the correlation between compactness and black hole growth, we find a clear relation there. Here is the relation that we find. This is, again, black hole accretion rate versus galaxy compactness in 3 different redshift ranges. And we find a pretty clear correlation at low redshifts from the Cosmos field, shown in black, and then at higher redshifts from the CANDLES fields, going out to redshifts of 3, we find evidence for a clear correlation there. This correlation appears to be a fundamental one. It's not merely a secondary correlation induced by something else. We've done partial correlation testing to check that. And notably, we find this clear connection for star-forming galaxies where we do not find it for quiescent galaxies. That suggests, as I mentioned, that gas density may play an important role in establishing this connection. Of course, galaxies that are gas-rich will be the ones that tend to feed their black holes. Okay, and so that's how you could imagine such a relation coming about. And then furthermore, the redshift dependence of the relation can also be understood via evolution of gas in galaxies. We know as you go to high redshifts, galaxies become more gas-rich. And using rough quantitative estimates of that increase, we believe we can plausibly explain this increase at redshift between the black hole accretion rate compactness relation. We are continuing to try to investigate this additionally with more ALMA observations. ALMA is very important with this. And I also would just want to note that this type of a relation can help to explain some of these so-called supermassive black hole monsters. There are a set of galaxies in the local universe where the black hole is much more massive than you might expect, given the bulge properties. These are outliers from the general trend. Notably, many of the outliers from the general trend are the galaxies that tend to be highly compact. And this connection between black hole growth and compactness may help to explain those outliers. So that's another important, connection to black hole growth. And there are many more things I could say about black hole growth versus galaxy properties, but there's limited time here, and you can check the relevant papers if you're interested. I want to talk about one other topic briefly before I get on to future work, and that is, I would like to say a little bit about supermassive black hole growth in the first galaxies. And this is work that Fabio Vito, an excellent postdoctoral researcher at Penn State, has worked on with me. Fabio did a lot of work constraining the space density and the obscuration fraction at high redshifts for moderate luminosity AGNs, the ones that we can uniquely probe with these very deep X-ray observations. And what Fabio finds is quite remarkable. He finds that the space density of moderate luminosity, shown in green, and low luminosity, shown in red, active galaxies actually decline toward high redshift, and they do it, if anything, at a faster rate than the high luminosity systems decline. That is a remarkable result, because you might think that in the early universe you would start with small systems and they would merge hierarchically to make bigger systems and so on. But if anything, if these trends persist, even at very high redshifts, the most massive things will outnumber the low luminosity things, which makes a challenge toward where they come from. It may be that you need some sort of a jump start via direct collapse to explain the frequency of the massive black holes. This also has implications for Athena and how many moderate luminosity active galaxies will be found at very high redshifts with future X-ray missions. And we also have constrained the obscured fraction. And here we can only measure quite high obscuration fraction, because as I said, as you go to high redshift, the X-rays are so penetrating, it's hard to stop them. And so we can only actually measure obscuration at levels above 10 to the 23, but we find that, in fact, there is a high obscured fraction where something like 50 to 60%, our best estimates are these completeness corrected values here in black. Our best estimates are something like 60%, 70% of the active galaxies at high redshift are obscured by large column densities, which is quite interesting. Now, we would like to push these types of constraints upon high redshift black hole growth even further. Right now, we're constraining things like moderate luminosity systems, at quite high redshift, but we would like to actually push back to even earlier cosmic times. This is very challenging, even for Chandra. So we've had to utilize, a bit of a trick to do it. And the trick that we've utilized is stacking, where we take the X-ray flux from large numbers of galaxies at high redshift, we add them up, and we try to get an average constraint on how much black hole growth is occurring in these galaxies. So I'll say a few words about stacking. This is a very nice plot made by one of my graduate students. It's the romantic example of stacking. So Brett, one of my graduate students, wanted to demonstrate the stacking technique. So he took 30 T candles, he put them on his stairs, here they are, and he took two photographs, one with a 3/100-second exposure, shown here, and here's a typical candle with a 3/100-second exposure. And then he took a 1/1000-second exposure of the same candles. You lose a lot of information because the exposure is shorter. That's what you see there. But if the whole idea of stacking works, you should be able to stack up the images of these 30 candles, registering them appropriately, and recover an image that looks like this. Well, and here, down here, is the stacked image of the 30 candles. Okay, this is 30 candles, each with a 1/1000-second exposure. You can see that you can pull back up from the individual low signal images, you know, the candles wax. You can see the flame very nicely. You can see some evidence even for the wick. And so stacking seems to work, and we use this exact same technique for high redshift galaxies. So what we do is we go to the 7 megasecond Chandra Deep Field-South, and we take samples of galaxies, and we have between about 100 and 1400 per different redshift bin, and we then stack them in the X-ray, and we try to either get average X-ray detections or upper limits. And in fact, we get useful average X-ray detections now up to redshifts of 4.5 to 5.5, and useful limits at higher redshift. In fact, here are our stacked images. Okay, in this one here, for example, this is considering galaxies of all masses. And we look at, in this case, we look at redshifts of 3.5 to 4.5. This is where we have 1400 high redshift galaxies. We stack them up, each one of which has a 7 megasecond Chandra observation. So the stacked image corresponds to an 8.2 gigasecond Chandra exposure on average. That's a 265-year Chandra observation on average. And you can see we pull up a signal from those galaxies. Here is higher redshifts. This is our 2.7 gigasecond observation at redshifts of 4.5 to 5.5. We pull up a detection there. And then at still higher redshifts, the numbers become smaller. The average exposure is shorter. We get only a very tight upper limit right now. And then down here, it shows the most massive half of the galaxies. And you can see most of the signal comes from the most massive half of the galaxies. And when we diagnose then what we think this signal is coming from, our best estimate is most of the X-ray signal that we're seeing right now appears to be coming from high mass X-ray binaries in these distant galaxies. We can estimate the star formation rates of these galaxies. We know that's correlated with X-ray binary production, and we believe high mass X-ray binaries are making most of this X-ray flux. And then when we constrain our measurements, which basically are shown here, these are our direct detection measurements as the large black symbols, and these open symbols are our stacking constraints. We find that our measurements are well below what many previous predictions were as to how much black hole accretion there would be at high redshifts. And furthermore, from the fact that the individual detections are greatly producing more power than the stacking, that tells us that most high redshift supermassive black hole accretion occurs in a short AGN phase, and that you can't hide a lot of additional accretion among large numbers of low accretion rate systems. We are presently working to push this to even higher redshifts. We've done stacking, in fact, up to redshifts of 8, and we're very excited about the James Webb Space Telescope results. James Webb Space Telescope is soon going to provide us with large samples of galaxies at higher redshifts with better redshift identifications and with better removal of low redshift interlopers. And once we have a much bigger and purer sample of high redshift galaxies, we can go and stack them. And we hope to push Chandra stacking analyses up to redshifts of like 10 to 15 with the samples from the James Webb Space Telescope. And then we will be able to set very good constraints on where the first supermassive black holes came from, because we'll be able to measure how much growth is there in all the galaxies that are out there at high redshift. And so this will be exciting for the future. So I would like to wrap up today by telling you about some future prospects for X-ray surveys of active galaxies. First point I want to make, the first point I want to make is that both the Chandra X-ray Observatory and XMM-Newton are still healthy. They're working great. This plot here is a recent summary of the various subsystems of the Chandra X-ray Observatory, and they're all operating pretty well. And in fact, it appears that both Chandra and XMM-Newton can likely last until like 2027 and beyond. So we hope for at least 5 years and perhaps much more of additional X-ray surveys. And now that these missions have been going for like 23 years, I think personally it's time to take on some big aggressive projects with them, take on some really big things that wasn't possible to do in their early years to keep exciting science, flowing from them. And so in fact, I put in a proposal for a big aggressive project. It was called XMM-SERVS, and it was to essentially use the XMM-Newton Observatory, which is superb at conducting efficient moderate depth surveys to get X-ray coverage of the LSST Deep-Drilling Fields. And so, of course, you all know of the Rubin Observatory, which is aiming to commence full science operations in 2024. I think the main survey may now be starting in January of 2025. And it will conduct a legacy survey of space and time over 18,000 square degrees. However, in addition to its general survey, it has picked a few sky areas as its deep drilling fields that it will observe with a much higher cadence and to much greater sensitivity than the general regions of sky over this 18,000 square degrees. And the regions are listed here. These are the 4 original deep drilling fields. One more has been added. They are the Cosmos field, the XMM-LSS field, the Chandra Deep Field-South, the field I've been talking about for much of this talk so far, and the LSS-1 field. Each one of these will be covered with a 10 square degree coverage, because that's the Rubin field of view. So these large black circles show the Rubin coverage, and then all of these colored shapes inside of here show the available multi-wavelength coverage we have in these sky regions. And Rubin is likely going to be observing these sky regions like every 2 to 3 nights in the GRIZY bands over 10 years. So we'll have superb variability data, for example, and it also will observe the U band whenever it's able to have the U filter in its filter complement. And SERVS, by the way, the name of this survey, SERVS, is the Spitzer Extragalactic Representative Volume Survey. This essentially is the best multi-wavelength regions down inside of these deep drilling fields. And so I put forward a program to use 5 million seconds of XMM-Newton time via a multi-year heritage program to get excellent X-ray coverage of 3 of the Rubin deep drilling fields. Cosmos already had excellent X-ray coverage. And we have now successfully covered these 3 sky regions over these solid angles as listed at a uniform 50 kilosecond depth with XMM-Newton. We have detected 10,200 AGNs, as well as large numbers of groups and clusters in these sky fields. And we are using these data in the short term to investigate like supermassive black hole growth across the full range of cosmic environments, because these fields are large, sample a wide range of cosmic environments. That's what's shown with this backdrop, which is a simulation of cosmic structure at a redshift of 1. And you have multiple fields that are widely separated on the sky, so you can beat down cosmic variance that way. We are also, of course, using the superb multi-wavelength data to investigate supermassive black hole galaxy connections as well. And the great thing about this is it allows exciting science right now. And furthermore, the X-ray AGNs we've now selected in these fields will serve as an excellent ground truth sample of AGNs that we can use to calibrate the selection of AGNs with Rubin. And that can be done in the deep drilling fields initially. And we can then take what we know of the deep drilling fields and we can scale it up to the full 18,000 square degrees. And in total, we're aiming to detect something like, 30 million or more AGNs in Rubin. But it's all going to be trained based upon this sample as our calibration sample, which is X-ray validated. And so this should be, very exciting, for the future. And as I'll say in a minute, there's a lot more multi-wavelength data coming for these fields as well. So here are the X-ray observations of these fields. And these are wide sky regions. For perspective, I put the size of the moon in each image. Okay, so these are wide sky fields. And we have 2 catalog papers, one published in 2018 for XMM-LSS and one published in 2021 by Qingling Ni. And because these fields have excellent multi-wavelength coverage, we have 88% of the sources having good multi-wavelength counterparts already. and we already have 70% of the sources with spectroscopic or high-quality photometric redshifts. And so we're working to develop this sample because this will have excellent complementarity with Rubin. And to put things in perspective, here is the wide field panoramic X-ray imaging. We now have over 4.6 square degrees of the Chandra Deep Field-South, and the Chandra Deep Field-South, that ultra-deep Chandra observation that I've talked about for much of this talk, is this little sky region down in here. And so now we have a broader perspective all around the Chandra Deep Field-South that we're going to use in complementarity with Rubin. We've done a lot of work, getting all the X-ray catalogs out to the public. They're all available to everyone. Here is the website where you can get everything. And we've been doing a lot of additional work. For example, we have recently done extensive spectral energy distribution fitting for all the galaxies and all the AGNs in the deep drilling fields. We utilize the SIGAL code to do this. And we essentially uniformly extract and fit SEDs and characterize them as galaxies, as AGNs, or as bursting and quenching galaxies. This is work that's been led by my current graduate student, Fan Zhao. The X-rays help greatly in the SED fitting, of course, in setting the level of the AGN component. And this allows improved source classifications, as well as measurements of host galaxy properties, like stellar masses and star formation rates, which we can then correlate with black hole growth. That's what we're going to do next in these regions. And we can calibrate, of course, off these small sky regions. There's superb calibration because, for example, we have the Chandra Deep Field-South right here. And so we analyze these data with our wide field approach, and we then compare it to the extremely high quality narrow field measurements. And we get good correlations between, for example, stellar mass and in this case, star formation rate, showing that we can do good measurements of these quantities. We also have been doing radio AGN selection and characterization. My recently graduated student, Shifu Zhu, is leading this work. And so in addition to all the X-ray AGNs, Shifu has studied those three fields, again, Deep Field-South, LSS-1, and XMM-LSS, and has selected large numbers of radio-selected AGNs based upon radio morphology, based upon radio spectral index, and based upon radio excess. This is a plot showing the radio excess, with these sources being the ones that are the AGNs. And you can see that radio selection selects a large additional population of AGNs, which are the low accretion rate, kinetic mode AGNs that are not very effectively selected by the X-ray approach. So we're getting a complete sample of X-ray AGNs, radio AGNs, and also mid-infrared AGNs, which come out of the SED fitting. So we're getting, the best possible sample of AGNs to get ready for the Rubin Observatory here. We also are selecting highly obscured AGNs. Vivian Yan in my group is currently doing this. She has found a large number of highly obscured AGNs based upon X-ray spectral fits, based upon the spectral energy distribution fitting, and based upon consideration of correlations between, for example, X-ray and 6-micron luminosity. And we find large numbers of obscured AGNs that will be exciting to investigate in the future as well. And then, of course, these fields not only have Rubin coming, but have a lot of other fantastic data coming in the near future. There's a large number of spectroscopic surveys. Devils is currently ongoing, getting large numbers of spectra in these fields. Sloan 5 is doing reverberation mapping to measure direct black hole masses in these fields. These are the same fields where we have the X-ray coverage. Moons is going to do a massive spectroscopic survey over some of these fields, as will PFS and foremost waves. So there's a ton of spectroscopic data that's coming in the near future, and we're trying to get these surveys to target our X-ray sources. So we'll have excellent spectroscopic follow-up of all the X-ray sources. There also is superb radio data coming from the MEERKAT MIGHTY survey. TolTEC will perform excellent sub-millimeter mapping with the LMT. And of course, ALMA will be able to do excellent follow-up of the sub-millimeter sources. So there's a lot of fantastic data coming that can be used in conjunction with the X-ray sources. And I will end, because I see time is getting short, just by saying a few words about new X-ray missions. We, of course, want to extend these surveys even further with new X-ray missions. And there are a number of possibilities there. First of all, eROSITA, you probably know, operated for a couple of years before it was shut off due to the Ukraine conflict. But we have excellent all-sky surveys. I think they've detected like 2 million AGNs already with eROSITA. And there's a ton of work still to be done with all the archive data that have been gathered by eROSITA. Furthermore, the Einstein probe, which is being led by China, will do an excellent time domain survey of the wide field array areas of the sky, letting us study new transient sources, like some of the ones that, in fact, we found in the Chandra Deep Fields. And I am presently working a lot on an exciting mission called StarX, which is the Survey and Time Domain Astrophysical Research Explorer, which was recently selected as one of the mid-X missions that will have a Phase A study. And we are competing against one other mission right now. And if we're selected, we'll be funded at about a $300 million level for a 2028 launch. And so we hope to have a new powerful X-ray mission that will do excellent surveys. And we'll also do a lot of exciting time domain work. And of course, we're also hopeful about the Athena mission, which is now being rescoped into New Athena, which we hope will launch like the mid-2030s. And, you know, the combination of StarX and Athena will let us conduct surveys like the Chandra Deep Fields, but over much larger solid angles, giving us much larger source samples. And so we're quite excited about that as one, you know, possibility for the future. And so with that, I will wrap up. And thank you very much for having me. And I'm happy to take any questions.
Thank you, Neil. Excellent talk.
Thank you.
Open to questions.
I have one after the student.